I'm going to give the second talk today on randomness, so on proofs of delay and randomness beacons in Ethereum. And this is joint work with Joe Bernoulli and Stephen Goldfeder, who's also here today. So anybody who was here yesterday saw the lottery, and Philip already used this as an example, but as you saw, right, like the blockchain guys, blockchain at Berkeley, they won like 5 out of 6 of the prizes, and like big bias alert, as Fox News would say. So the thing is, we saw already with RandHound and RandHerd, how could you solve this problem if we all got together and in a very efficient protocol, in the nice talk that we had earlier by Philip, like we could all communicate and find a randomness beacon together. But let's think about another example. So here I got this email a couple days ago that I won tickets. I was very lucky to see, actually this is long ago, but to see Ruth Bader Ginsburg, the Supreme Court Justice. But what if she, right, like she wants fairness, and she wants, what if she would like to verify that I actually won this ticket honestly, because it says I was randomly selected, but what does that even mean? Does it like, do I maybe have a friend in the ticket office who helped me out here, or like what happened there? And what if RBG, who wasn't there to oversee the lottery, what if after the fact she wants to verify that the beacon was generated randomly? So we want this global, publicly verifiable randomness, such that anyone, even if they weren't there, even if they didn't participate in selecting the randomness, could verify after the fact that the randomness was generated fairly. So this is important in general for all these algorithms where we want to verify that execution was done correctly, right? Like you can maybe with a snark verify that the algorithm was followed correctly, but what if the seed that was selected to run the algorithm was biased or was chosen properly? Right now it's really hard to figure out like why was this really a random seed, but we need to do this to verify that an algorithm was run correctly. So for example, that a lottery was run correctly. So who provides this randomness? Is it a trusted source, a group, or can we really have this global, public, verifiable randomness? So what are sources of randomness? What do we do in the real world? We do these public displays, right? We do a drawing out of a bag, but they're very simple to understand, but they're also very difficult to verify because, like, say, someone is shuffling cards and deals me a hand. If he's a magician, right, I could be completely fooled, but and there's no way for me to really tell. And this actually happens in practice. So here's this example of this Serbian lottery. And you can see that 3 balls are drawn, or 4 balls are drawn, but like 5 are already down here. And then it turns out that the next 2 numbers are actually 21 and 27. And you should Google the video. The reporter looks very confused, and then looks even more confused. And you can tell that something went wrong there, and wasn't just the display of the graphics. And yeah, it's quite funny. Or if you're into basketball, or like for the international people here, the FIFA like drawing of the tournament, there's always like big controversies. So for example, in '85, the Knicks got Patrick Ewing, and people are still claiming that this was done to like make the Knicks better, but they still suck. So. And like there are a bunch of theories, right? Like that the envelopes that had the Knicks pick was like frozen, such that you could feel which one it is, or that it had a bent corner or something. I don't know. Like, well, but like the truth of the matter is, right? Like it's really hard to actually check what's happening, and like you might believe David Stern, but like you might also think, well, something is going on. And so what we really like is these cryptographic, or what we have is these cryptographic beacons. So we want a service that randomly publishes this really good and like solid randomness in regular intervals. And this has, as I already said, this has many applications beside lotteries, so auditing, zero knowledge proofs, and so on and so forth. And you can also use them in smart contracts in many different ways. So what are the properties of this beacon? So we want it to be unpredictable. That's one of the main properties. So before some time t0, where everybody buys the lottery tickets, no one knows what the value of the beacon will be, right? And then, but at some point in the future, an honest beacon provider can always convince an observer of the correct beacon value. So I can tell you, I can convince Judge Ruth Bader Ginsburg that this is the correct beacon. And then we also want it to be unforgeable, or that no one can produce a fake beacon that convinces the verifier. So what are the engineering goals? We want that we have high bandwidth, we have frequent publication and rapid consensus, and it also it would be nice if it has low cost. But in general, one of the main problems that we focused on is this public confidence, that like it's really globally verified. So one tool that we have right now is this NIST beacon. So NIST runs some quantum experiment or something, measures that, publishes its value, but you really have to trust that the NIST beacon was generated correctly, and it's completely centralized. So it kind of fails the public confidence if you don't trust the NSA or the NIST. So we really want to have no trusted party. That's one of the requirements that we have. So this seems hard, but the amazing thing is that Bitcoin or blockchains are coming to the rescue, because it already fulfills, like, by itself a lot of the nice properties that we want. So it's decentralized, there's consensus is reached, there's a continuous publishing of things, and there's this inherent broadcast mechanism. So we assume that everybody sees the same blockchain, or at least after some time of convergence, everybody agrees on what the same blockchain is, and if I put a message on the blockchain, then everyone will see it. So, and then there's this other nice property, is that proof of work solutions are inherently unpredictable, and I'll go into a little bit more detail on that in a second. So let's recall the blockchain format for a second. So, right, you have these it's this chain of blocks which all link to each other. So the next block contains a hash of the previous block, and then what it also has is that you have this nonce, right? This freely chosen value, such that the hash of the block starts with a bunch of zeros. So right now it's like over 70 zeros, I think, in binary format. Or so how can we turn this blockchain into a beacon? Well, we can look at the nonce, right? Like, you can't really choose the nonce freely. Say I want to have a certain beacon, I can just say this is my nonce, because it's likely not going to lead to a hash that actually has 70 zeros. So what if we just take this nonce, like the first strawman proposal is just to take this nonce, or take the hash of the block as I use a different hash function in extractor, but you basically use the entropy that is in each block and the nonce of each block. So we can, extract the randomness from the block, and we can. It turns out that you can extract like as many bits as the difficulty is, because because the thing is that if I could predict the next beacon, if I'm an honest miner, if I can predict the next nonce with greater probability than the difficulty, or 1 over the difficulty, then I actually have a mining shortcut. Then I could use that, right? Like if I know, okay, like if I can guess randomly, and then I have a 1 over a million chance that this is a valid nonce, then I could mine a lot faster. And we assume that there's no way to mine faster. We assume that the hash function is secure. So therefore, each valid block has 2 to the d bits min entropy. So right now, over 2 to the 70 bits of entropy, or 70 bits of entropy. But this is only true if miners follow the default protocol. So if we have honest miners, or miners who are following the protocol, then we get these 70 bits of entropy, and we have a good randomness beacon. So is this secure? Well, no, it isn't. Because as a miner, say I mine a block, right? And I also participated in a lottery that I really care a lot about, because I can win $1 million. If I mine a block, I can decide whether I publish it or not. And if I see the block and it's a winning lottery ticket, then of course I'm going to publish it. If it's not, then I'm just not going to publish it and try to find another block, or maybe someone else will find a block that wins me the lottery, right? So with this withholding attack, I can manipulate the beacon. So, okay, with a completely adversarial miner, this is not secure. But in the blockchain in general, we deal with rational adversaries. So can we maybe say that, okay, it is possible to attack, but there's a big cost to attacking, or what's the cost on attacking? So can we bound the costs of manipulation? So let's assume a rational miner. So the attack, you can also think of the attack, what if I'm not a miner, but I still want to manipulate the beacon? Well, then I can use you can think of it as bribery in general. This also works. An attacker uses bribery, because I'm just going to say that here, if you find a block that doesn't win me the lottery, I'll pay you the block reward, or I pay you a little bit more than the block reward if you don't publish it. So so this covers an attacker who's a miner, but also an attacker who's a mining pool, or an attacker who has no money but just wants to influence the beacon. So currently, to influence a block, so to basically manipulate a block, this costs me roughly one block reward, so $55,000 in Bitcoin and $1,500 in Ethereum per block. So this might be, if I have a low probability of winning overall, then this might already be good enough. If only 1 out of 1 million tickets wins for me, then this might be good enough. But what if there's a protocol where I win every second time? So coin flips are really the difficult one, right? And coin flips, I might only have to do influence a single block, and then I already win. Or what if there's I only need a slight edge. So I'm playing in a casino or something, and I only need to gain that little bit extra edge to make this thing profitable for me. So what can we do here? So the solution that we came up with is a so-called delay function. What if the attacker, once he finds the block, has no way of knowing if this is a good randomness beacon for him? What if he doesn't know, or what if he can't compute the value of the beacon? What if he can't evaluate what the value of the beacon will be for him, so whether he will win the lottery? So how can we enforce that? The way that we enforce that is by saying that the beacon is only computed, depends only on the block, but it takes, say, an hour to compute what the actual value of the beacon is. So you run this long and slow computation that takes an hour, and only then you know the value of the beacon. So I have no way of knowing, so I can find a block, and then I have to do an hour-long computation to figure out what the value of the beacon is, and only then I can decide whether I publish it or not. But the problem is then the blockchain has already moved on, and my block will be invalid. So I've lost my opportunity of publishing the block, because there's continuously new blocks are being published, and my block or my nonce is only valid now. So if I don't publish it right away, then I've wasted all this energy, right? I've wasted real resources on trying to influence the beacon, and I haven't even influenced the beacon because the blockchain has moved on. So so we want this delay function that takes some input and some time and then computes an output. So what is this, what does it mean to have a delay function, right? What are the properties that we need? So we kind of need that it's entropy preserving, but the most important properties is that it is sequential, right? Because say we have something that takes a lot of resources, but is highly parallelizable, like factoring a number, for example, then how do I know, how can I even say this takes an hour to compute? What does that mean? Someone who has a large server farm will take a lot longer than someone who operates on a single core. If, however, it is a sequential computation, then we kind of know, right, they're bounds to how much you can speed up the clock speed of a processor, right? So they're physical bounds, or they're much more limiting. So you can't just scale up the computation. If it runs on a single core, and it takes 1 billion 2 to the 40 cycles on that single core, there's a limit to how fast you can compute this. And so we want basically the sequentiality that we want, or the time that we want, depends only on how much sequentiality we get. We also need it to be absolutely deterministic, right? You can't use a proof of work, which is, by the way, also parallelizable, but you can't use a proof of work because it's not deterministic. There are many solutions, right? And if my delay function has many solutions, then I can pick the one that gives me the best beacon. I want there to be only one solution and one solution only. And then also we want, we want it to be still, though, very succinct, so a short thing that I can verify efficiently, right? So I don't want to verify by rerunning the delay function. Ideally, I would like to be able to verify this in a smart contract. And on top of that, it would be nice if it doesn't have a private setup. So, and this delay function has many other uses, which I won't go into. But a simple delay function is just a hash chain. So you just compute, say, 2 to the 40 hashes on the input, right? It's clearly deterministic, right? If I can, to find 2 different outputs, I would need to find a collision on the hash function, which we assume is hard. The problem, though, and it's clearly sequential, there's no way for me to parallelize it other than parallelizing the one step of the hash function. And the verification, the problem is that the verification is exactly the same as the proving time, right? To verify it, I just need to rerun the whole computation, so it doesn't have an efficient verification. So it turns out that what we want is the so-called verifiable delay function, and this is actually kind of still an open problem. We have some forthcoming work on this, and we have some candidates, but they still have limitations. So if you have ideas on kind of like it's it's a simple problem to state, right? Like you want basically a hash chain with a succinct verification. And if you have great ideas on this, please come to talk to me. So we have some ideas based on recursive snark composition and another one on factoring polynomials, so inverting polynomials. But this is forthcoming work, but I have to say that both of these solutions still have some limitations. So they aren't optimal. So what can we do with let's think about again the hash chain. Well, what can we do with the hash chain? And luckily we heard a whole talk on basically what we can do with hash chain in the TrueBit talk before. We can use this referee delegation model, which Canetti and Rira and Rothbaum came up in 2011, which is this interactive verification. So I compute my proof of delay and put the input and the output on the blockchain, and then you can do the same thing. And if you believe that I made a mistake, right? If you believe that I cheated, then we can run the TrueBit kind of, or the TrueBit-like, or this referee delegation model where we find the point in the hash chain that we disagree on. So we find this one point, right? And then the smart contract, all he has to do is at that one point compute one hash check. So what does this look like? So we say like, okay, I'm going to post. I can also post a couple values. So I'm only going to post like n values, and each of these n values is 2 to the 20 hashes between them. Okay. And then someone can, in parallel, check whether all these things were done correctly and say that, oh, wow, xi, if I apply 20 hashes to xi minus 1, I get a different value than xi. And then the prover says, yeah, well, prove it. Okay. Then he's going to take 20 values between xi minus 1 and xi, or he's going to post, right, 2 to the 4 values here and 16 values here, and say like kind of do the same step as the guy before and say, okay, these are my intermediary steps. And the prover, if he still thinks he's right and if he didn't actually cheat, he can say, well, I actually think that you made a mistake here between xl minus 1 and xl. And so on and so forth. And then the smart contract, at some point, the computation is so small that the smart contract can do a direct computation and verify what the value is between zi minus 1 and zi, and say if the prover or the challenger who was right here, right? And based on that, we know what the beacon will be. So we actually also implemented this and showed that this is possible to do in Ethereum. So, and the nice thing is, so we don't have to worry, right? Like the hash chain gives you a very simple mode of computation. So a lot of the stuff that TrueBit has to worry about with like general computations and mapping a Turing machine into some circuit or whatever, it does not apply here, because here it's clear, right, that every single step is just hashes. And we actually don't just use a hash function, we use something slightly better, which are square roots modulo prime, because they have more succinct verification than computation. But as we also heard in the last talk, and please refer to the paper for more details, the incentives matter. And here the incentives are especially interesting because the beacon is a public good, so everybody benefits from it, but it's really hard to sell it, right? Like there's also no DRM on a beacon, right? Because if I produce a beacon and give it to someone along with a proof that it's a verifiable beacon, right? Then this person, even if I'm able to charge one person for it, he can just sell it off to the world, or he can make it free, right? It's like an MP3, you can just copy it. So we kind of, sure, we argue that you likely need a foundation to actually provide this as a service, but once it's there, everybody can use it. It's a public good, right? It's like a lighthouse, right? Anyone can benefit of it, even if just one person computes it. So yeah, and right, providing an incorrect beacon should be disincentivized. Challenging incorrect beacons should be incentivized, and so on and so forth. So what are some of the open problems, right? The cost of attacking is actually really hard to measure, because what if I run a $50 billion lottery based on this beacon? Then an attacker might be willing to destroy, right? Like the incentives intermix with the incentives of Bitcoin itself, right? I might be able to do a deep fork in Bitcoin to fix the beacon, but at the same time, I'm going to destroy like Bitcoin or the security model of Bitcoin. So the attacking the beacon is going to be less costly than attacking Bitcoin as a whole. But also, if I attack beacon and the beacon invested a lot of mining power in it, right? Like, wouldn't I just spend this mining power on mining Bitcoin and get the incentives through that? So yeah, so is there a limit to attacking the beacon? Is it equal to attacking Bitcoin? So it's very, very hard to compute the precise cost of what the actual cost is of attacking the beacon. But at the very least, we're trying to give we're able to give a lower bound on what the cost is. Another problem is what is the power of the attack, right? Like we've seen in Bitcoin how much hardware improvements can do to optimize, right? Like with the hash functions and with ASICs, we can see how much hardware improvements can do to speed up the computation, right? So this is especially done through parallelism, and we don't have the idea of a proof of delay is that you don't have parallelism, but it's still really, really hard to say like what is a computation that takes an hour. And there's also these, you can get into crazy things, like there's these graphene chips that are 10,000 times faster than a normal processor, and what if someone decides to invest a lot of money and build a chip like that? But in the end, the takeaway is that smart contract beacons are feasible today, and we have code on that, and we have a paper on it, and you can read about it and use it. And that any verifiable beacon is a security upgrade over what we have now. So that if you use, right, like for any of these lotteries, like, and any of these that are happening in the real world, right? Like, so for example, there's also a green card lottery, which is really important for many people who are trying to get a green card in the US. And all these things, it would be better if they used a verifiable beacon, even if there's still questions about what the true cost of attacking is, because at the very least we can give a lower bound to saying there's a real and it's really expensive to actually manipulate it. So any verifiable beacon is a security upgrade over what we have now. Well, yeah, thank you very much, and here are the links to the paper, and yeah.
Any questions? Who has the box, the microphone? You want to send it to him?
Thanks. So how do you pick the 1 hour delay? How do you know that that's the optimum amount of delay? And the consequential computation does not serve as a bottleneck potentially?
Sorry, Ed, can you say that again?
The sequential computation that steps in delay, don't you think that would be a bottleneck on the blockchain? 1 hour, how do you pick that?
Oh, that's well, okay, so the 1 hour was an arbitrary number. Yeah. So the longer you make the delay, the more difficult it becomes to attack, because the attacker will need to fix more blocks. So you should measure it in basically the number of blocks that are in between. So you would have to say, right, and we know that basically we know basically what the cost is for fixing one block. It's like, or for manipulating one block. It's like, say, $1,500 in Ethereum, and then you can estimate, right? Like, I have $1 million riding on this computation, and you have to make estimates for how much it costs, how much an attacker can benefit by manipulating it, and how much money is riding basically on the beacon. And the more money is that is depending on it, the longer you want to make the delay. But obviously a long delay is kind of annoying because you have to wait for the outcome of the lottery. So yeah, it really depends on what your application is.
So the time can be changed based on the use
Oh yeah,
cases.
yeah. That's just you just kind of say like how long, right? Like for example, for the hash chain, you just say how many hashes do you have to do for the proof of delay, and based on that, it will take a longer time or a shorter time.
Anybody else?
Thanks for your talk. Actually, we already had a talk today about publicly verifiable randomness. Yeah. Why do you think your approach is better? What's the differences?
I don't think it's better, but I think it's a different setting, because in the Randhout and Randherd paper, it is in the Byzantine setting where you have n parties, and you say that a threshold of them T is honest. And then the question is, how do they very efficiently compute a beacon together? So we don't assume any honest parties. We just assume that the Bitcoin blockchain work, or whatever blockchain you use works, and whatever rational, so the proof of work, so whatever rationality assumptions are encapsulated there, also encapsulated in our beacon. So we deal basically with rational attackers, whereas the other paper deals with completely adversary attackers. But on the other hand, you need an honest majority or an honest subset in order to get the beacon. And it's really more for a large group of people. And this is supposed to be a global beacon for the whole world, I guess.
Okay, thanks.